Okay, folks, we just discussed kind of the step before the citric acid cycle, the pyruvate dehydrogenase complex. So, glycolysis gives us pyruvate. The pyruvate dehydrogenase complex gives us acetyl-CoA. Let's use that acetyl-CoA as we learn about the TCA. We will discuss 8 enzymes that perform a wide variety of reactions. Enzyme number 1 of the TCA is performed by citrate synthase. It performs a condensation reaction of acetyl-CoA and oxaloacetate. Its conformational change is kind of like hexokinase in that we have this kind of open mouth structure, and then substrates bind, and you can see how the enzyme is kind of closed in on itself to exclude water so that the reaction can proceed without water getting in the way and messing things up. I'm showing you the actual reaction on this page here because it's interesting to look at, and there are similarities that I want us to look for. Remember, we don't need to be memorizing these mechanisms or reactions. I'm pointing out similarities so that we can be understanding kind of big picture ideas here. You're going to see both acid-base catalysis and some electrostatic stabilization. So let's orient ourselves to the beginning here. We have one substrate, oxaloacetate, and our second substrate, acetyl-CoA, down here. Aspartate performs an acid-base reaction and is grabbing this proton from acetyl-CoA. So it's a base catalyst grabbing that proton. That leaves us with a negatively charged reactive intermediate, folks, that is stabilized by hydrogen bonding with this histidine in the active site. Now, of course, you see this negatively charged oxygen, or, we could resonate that lone pair onto the carbon to have a negatively charged carbon. We should remember from organic chemistry that carbon is a better nucleophile than oxygen. So when we collapse back down the reactive intermediate, we have nucleophilic attack of this carbon to the biochemist's favorite electrophile, the thing that looks like the carbonyl carbon, right? At the same time, we have a histidine at the top of the active site that performs acid catalysis by donating a proton to the O-, which would be formed by the tetrahedral intermediate here. We're almost done, folks. So here on the top right, we have now a covalent bond between what was oxaloacetate and our acetyl-CoA. We have some nice hydrogen bonding, stabilizing and binding to our substrate. The last thing we need to do is hydrolyze CoA off of this structure. So in comes water. We chop off CoA. Leaving us with citrate. And that is step 1. Again, showing you the mechanism so that you can see similarities, not so that you can memorize all these details. So now we have citrate. In step 2, the enzyme aconitase performs an isomerization reaction, really, moving the hydroxyl from one carbon, my head is kind of blocking this, to the carbon just below it. It is a dehydration reaction followed by a hydration reaction. And this is interesting reaction because we go from a prochiral molecule, prochiral just meaning not yet chiral, to a chiral molecule, which is super interesting. And I point this out, folks, because when we first learned about binding sites, I told you that their geometry, the binding site's chirality, was important. Well, a molecule, if it binds an active site, can become chiral because the active site itself, its geometry, matters. Additionally, I'm going to introduce us to a new cofactor that we haven't learned about yet, but we'll see a lot in the coming weeks, an iron-sulfur cluster. So this has 4 irons and 4 sulfurs in a complex together. We will see these in the future performing redox reactions, but it doesn't in the case of a kinetase. This iron-sulfur cluster, we think, likely binds to and is coordinating the OH that needs to be participating in this reaction. And we have already seen in this class how an iron cofactor can kind of bind to and polarize hydroxyls. The next enzyme is isocitrate dehydrogenase, okay? So we're taking isocitrate, which is the structure here that we just made in the last reaction, and we are converting it through a series of steps into alpha ketoglutarate. You can see that we are using NAD, so we must have performed an oxidation reaction. And indeed we did, because you can see this hydroxyl group is converted to a carbonyl. Additionally, you'll see that we use a metal ion cofactor. This manganese or magnesium can be used to polarize and stabilize this carbonyl oxygen, which is important for the mechanism to proceed, especially as you see that the reactive intermediate is negatively charged. Some more similar things that we've seen. Step 4 is performed by alpha ketoglutarate dehydrogenase. We go from alpha ketoglutarate to succinyl-CoA. So here we have an oxidative decarboxylation. So we decarboxylate but also oxidize, and we know that we oxidize because again we're converting an NAD to NADH. Here we've lost our second CO2. This product, succinyl-CoA, contains a high energy bond because you see that we've added a CoA, a thioester bond into the mix. And if we make a high energy bond, you might expect in the next step that we cleave that high energy bond to conserve and gather that energy. So enzyme 5, succinyl-CoA synthetase, couples cleavage of that bond to synthesis of GTP in mammals, which is our focus, of course, in this class. This enzyme, I think, is kind of interesting because what it does is upon hydrolysis of the CoA, it kind of converts that high energy bond into the formation of a high energy phosphoanhydride bond. And that phosphoanhydride bond is kind of shuffled from one group to the next group to eventually be used to synthesize GTP. So you can see that this phosphate is first forming succinyl phosphate to have this phosphoanhydride-like arrangement here, and then that's transferred onto histidine to phosphohis, and eventually from histidine to GDP to synthesize GTP. I thought that's kind of interesting. Next enzyme up, succinate dehydrogenase. So we have succinate converting it to fumarate. This process generates FADH2 because again you can see we've oxidized this single bond to a double bond here. And this enzyme is a rare example of an FAD that is covalently linked to a histidine in the active site. Many FADs aren't covalently bound in this way when they're used for redox. Next up, the enzyme fumarase. It performs a hydration reaction where we take this double bond and add water across the bond to make malate. Finally, the last enzyme in the TCA is malate dehydrogenase. Here we have the formation of the final molecule of NADH. So we take that water that we just added, we take that OH, the hydroxyl from the water, and we oxidize it to a carbonyl and form NADH. In the process of this, we regenerate oxaloacetate from malate. So you can see how we started with oxaloacetate and ended with oxaloacetate. This mechanism is very similar to lactate dehydrogenase, so here's a similarity in that mechanism that we've already seen today. And another interesting connection to glycolysis. Here's another example of a coupled reaction. So this reaction here from malate to oxaloacetate has a positive delta G. However, step 1 has such a negative delta G that step 1 is able to pull step 8 along through Le Chatelier's principle. To end this next video, folks, I'm going to quickly generalize that usually we'll see FAD used to oxidize alkanes to alkenes, single bonds to double bonds, and usually we'll see NAD used to oxidize alcohols to carbonyl groups. That is the TCA. So far we have seen glucose converted to 2 molecules of pyruvate, those 2 molecules of pyruvate converted to 2 molecules of acetyl-CoA, which then go through the citric acid cycle. We've seen a bunch of NADH made, some FADH2 made, and some GTP and ATP. What we will see once we learn about electron transport is that this oxidative metabolism makes a lot of ATP, which is great for us. Next up, regulation, and that will be the main focus for the rest of the videos.